What is the difference between programming languages? Like, why do we use different ones? Why can't we just write programs in a single programming language? Why are there so many of them? Well, in today's video, we'll go over 3 programming languages to explain how they function, what's the difference between them, and why we use them. But before that happens... So first, let's start by describing the operation of a factorial. What does it do? Well, that operation takes a number, multiplies it by the factorial of the same number, minus 1. Then on the next smaller number we perform the same operation, multiplying it by the same number, minus 1. And then again, until we reach 1, where we stop. I think most of you are already familiar with this operation, but the reason why I wanted to mention it here is because with that context we can describe it for our purposes to make a program. So, how would our programs work? Well, first we start with our basic number and another number we'll call a result, which will start equal to 1. Then what we do is we check if our number is equal to 1. If it's not, which it isn't in this case because 5 is equal to 5 and not 1, then we multiply the result by our number. We decrement the basic number, which just means subtracting 1 from it, and repeat the process. Then we keep going and going and going until our number is actually equal to 1, and then, there we go, the result is equal to the factorial. So let's try it with some kind of number like a 5, just to see the entire process. We take that number and another number, 1. Then we check if that number is equal to a 1. It is not, and as such we just multiply the result by the number, resulting in 5. Then we subtract 1 from the number, and then repeat. Check if it's a 1, if not multiply, subtract and repeat until it is equal to 1. At that point you can just take the result and there we go, that's our factorial. Now, how do we implement it in different languages? Well, first let's start where we finished off in the last episode, the machine code. So, what is machine code? As a quick refresher you can think of it this way. Imagine that you have 4 registers, 2 operations, and gates between them that pick which one we'd like to use. You can connect them all like so, and here's how it works. First, we start with 4 registers. If you'd like to know how they work, watch the previous video where I've built them from basic gates, but here all you need to know is that they store some kind of number. So here I'll just store a 0, a 1, 36, and 200. Next we'll have components which will select which register we'd like to use. Each one will have 2 inputs going into it and 2-digit number, where they can select if we'd like the first number, second number, third number, or fourth number, like so. And okay, I know that might be really difficult to see, so here's the same thing except this time color-coded. Now that's how we pick a number. Next we select which operation we'd like to use, so if we set our 2 numbers that we'd like to use something like a 7 and a 36, then here's how we switch between them. So here you can see color-coded how it would work. The first 2 digits of binary select which register, like so. The second 2 select the second register, and the last bit selects the operation. That way you can encode both operations between any 2 registers, that is the machine code, except in CPU you obviously have more registers, more combinations, reading from memory, saving to memory, jumping in the operation, tower protections, branch prediction, and you know what, we're just getting wildly off topic. The point is that this is where we'll start today's video. In this video we will implement this kind of algorithm in multiple different programming languages. And first we will start with machine code, and that's a bit of a big one, but basically... Hey, whoa, why are you here? Well, I mean, I'm just here to save you from the hassle of explaining machine code, because you want to write a program machine code, but in reality there isn't that much general knowledge in there. It's all specific to the architecture, and it just becomes a massive pain. So I basically want to stop you from going to that path of the future. I mean, okay, I guess that makes sense. Machine code by its very nature is very, very specific. So I suppose there isn't really that much of a point to go in depth. So where would you propose we go from... Oh, they're gone. You know what, sometimes I don't know if I can time travel, clone myself, or if I'm just schizophrenic. Anyway, what was I talking about? Assembly. So, remember those things I kept mentioning called registers? Well, in assembly we can access them using keywords such as RAX, RBX or RCX. These registers are the magical boxes that hold our values, and we can put some values into them using the move operation. Move is just the move without the letter E because it's more consistent to have all the operations be 3 letters long. It just looks nicer. And so with that in mind, we can actually start using it right away. If we write a piece of code that looks like this, then what this code effectively does is first, it moves number 1 into the register A. Then the second line moves the number 10 into the B register. Then the breakthrough. Third line moves the value from register A into register C. Now, the reason why the third line is such a breakthrough is because that's the kind of line that lets us do something like x plus 5 instead of 2 plus 5 or 6 plus 5. So basically a code that works depending on the circumstances, not with any hard-coded value. What do I mean by that? Well, let's say that you'd like to get a square of some kind of number, like a 2 for example. How could you do it? Well, you could do it by first taking a 2, then moving into the A register, then we can move the same number from A register to a B, and then we can multiply them both together using the IMUL operation, which just stands for integer multiplication. It has 4 letters because we don't need everything to be 3 letters long, and then the result of that multiplication will just be stored back into RAX. That's us squaring a 2. If we started with a 5, however, and then run the entire code, then we would end up with 25. So this is our number that we want to square, and this is the operation of squaring it. Now let's say, hypothetically, that for some unknown, totally not a foreshadowing, wild, crazy kind of reason, we have a number inside of RCX that we'd like to get a square of. Okay, it's just there already. Some kind of wizard already put it there using their sorceress techniques. Now, in order to get the square, all we need to do is just replace the 5 with RCX. And there, we've got a program that will actually take some kind of number and just compute the square of that number. And that's programming. Now, that's all neat and good, but there is something else we'll need in order to make our loop work, and that's 2 things actually. Conditions and loops. So how can we achieve those conditions and loops? Well, a loop is simple. In assembly, there are labels. You can just input something with an operation like so, and that actually does nothing on its own. The more you know. But the reason why it's useful is because of the jump operation, where once again we take out the u because, consistency. All operations are just 3 letters long. And what jump effectively does is it just moves us to some kind of label. So in this situation, for example, if we start at the top by moving a 1 into a register, then we move the value of A register into B register, then we jump to the second label, and then we move a 2 into the A register. We never move anything into the C register because we skipped that step by jumping. But the crucial thing to remember is that jump doesn't have to go forward. You could as well execute code like so. Then what this effectively translates to is us starting by moving 3 into the register A, register B, then multiplying them into A, and then go back to loop. Multiply again, go back to loop, and so on, so forth. We've achieved loops. There is one problem, however. These loops are permanent. Once you start a loop, there is no way to break it, and for that we'll need the second part, and that is the conditional. So, how do we set up a condition in assembly? Well, you can do it using the CMP, for example. That is compare, except once again shortened to 3 letters. What this does is just compares 2 different values. So for example, compare RCX with a 1, compares the value of RCX with a 1. Cool, how does that help? Well, it helps because on the next line we can specify that we'd like to jump somewhere, but only if the 2 numbers are equal, or not equal, or one of them is greater, or lesser, and it just keeps going. So that way we could have conditional loops. So for example, going back to our multiplication loop. Now this time this works in the exact same way, starting with moving 3's into A and B, and then the loop we multiply by 3 again, but this time we compare them. And when we compare the two, array x is not greater by 1000. That's because 9 isn't greater than 1000, so we don't jump. Then we jump back to the loop and 27 isn't greater, 81 isn't greater, and it just keeps going and going until we reach the smallest power of 3 that's greater than 1000. Then after we compare our register to 1000, it is actually greater, which leads to us making this jump, ending the loop. And so what we've done here is we computed the smallest power of 3 that's still greater than 1000, and we hold that value in our register A. Now if we just start by inputting our Cx instead of 3, then we end up with a program that can compute the smallest power of x that's greater than 1000. And now with that in mind, let's try our hands at a factorial. In order to do it, we first start with 3 labels: the func, buck, and loop. The func starts our program and sets all the values, and here's the values we'll need. The RCX register will hold the value that we want to take the factorial on, for which we won't need any code. That will happen before the program, the wizard foreshadowing again. And then we'll also need a 1 in the A register, which we can achieve with this line. I feel like that's pretty straightforward. Great, that's all the prep work we need. Next, after that, we start our back part of the loop, which compares our RCX with a 1. If they're not equal, then we jump to the other part of the loop. Now what this loop does is just multiplies our A register by the C register, and then decrements the C register. What decrement means is, once again, just subtract 1 from it. Then afterwards we jump back to the back of our loop and repeat. This is our factorial method from before, this time written down in a tad more stricter way. And so there we go. You should now understand how to make a program that calculates the factorial in the most difficult language in existence. Why? Well, for 2 reasons. First of all, I am amazing, and I was the one explaining it, so you're welcome. For the second, I mentioned that assembly is the most difficult language, and I can already feel the nerds telling me in the comments how about their obscure language is only ones and zeros, or dashes, or arrows, or colors, because why not? Is actually the most difficult language in existence. But here's the thing, having a weird way of writing is inconvenient at best, it's not really difficult. The actual difficulty of a language comes from something different, and in this case that could be easily showcased by asking a question of why the C register? Why does it hold the magic wizard value? Well, that's because the full program I've made also includes this C file. And you see, even though you know how to write an assembly, if I told you to make this program right now, you probably wouldn't know how to run it. You wouldn't know where to start. You wouldn't know how to turn this code into the machine code from before. So, how did I do it? Well, I used an assembler, which is a program that turns code from something that a human can read into something that a computer can read. But how can I get the output of our program back? Well, the way I did it is that I created a kind of wrapper around our assembly program in C, and I just created an external function that will be linked with the assembly function. And no, you're not supposed to know what it means. That's because the actual kicker here is that I know from that the variables inputted into this function end up in the RCX register after running it. How do I know that? Well, it's because 4 years ago, Drunk Maker delved into the documentation of C and assembly because they thought it would be funny to implement mathematics in assembly for the graphical engine. And that's why assembly is the most difficult. Not because of some confusing notation or because of weird walkings. It's because unlike other languages, assembly is so low level and so close to machine code that it actually runs into the limitations of our CPUs. When you can't do something in between the registers, it's because the CPU isn't able to physically do that, not because it's just some arbitrary rule in our programming language. And that is what makes it difficult. Anyway, speaking of C. Okay, so in C it certainly looks a tad bit different, but don't worry, it's actually quite manageable. First, we'll start by discarding the includes. They're not important right now, we'll focus on them another time, but the rest will actually leave. That's because this int main is kind of like our label from before. I'm saying kind of because it's a tad more complicated, I'll explain this more later on, but for now all you need to know is that I called it main because once we compile our program, this is where it will start. It will start at the function called main. You can think of the act of us starting a program kind of like running jump main, and so that's how the program knows where to start. Then we have the curly brackets, which just denote what's inside our function and what's outside our function, and then if you've seen my How Do Computers Remember video, then this should be pretty clear. Long is just an 8-bit long variable, and we create two of them. The first one is equal to the number we'd like to take the factorial of, in this case 5, and the second one is just a 1. Now what we do on the next line is a while loop, which, okay, remember the loops with the labels from the previous chapter? It's the exact same concept here, except this time we just package the whole label 1, label 2, compare, jump, if business with just a single while, with things on the inside of these brackets being the requirement for us to keep jumping. The way this works is that this will just repeat in circles, while whatever kind of logical statement inside here is true. So in a program like this, for example, what this effectively translates to is this right here is the decrement from before, so basically subtract 1, and we start our program with a char a in our memory, so a single byte which we set equal to a 10. Then we go into our loop and first we check, is a greater than a 5? Right here I'll put a little number to showcase what this binary number is equivalent to in base 10 to make this a bit easier, and yes, a is greater than 5, 10 is greater than 5, so we execute things inside of our loop. This is just the decrement, so we decrement the a, and now it's equal to a 9. Then we go back to the beginning of the loop, check if the statement is true, which it is, and so execute the inside, and repeat until it's no longer true, in which case we just move on. That's how a while loop works. Now in our case, what we do is we loop with this code on the inside, and what that code means is we just take our result, and we multiply set it to the number. Which basically means we just multiply the two and then set it to the result of that multiplication. This is just a quicker way of denoting it. And then on the next line, we just decrement the number. Then we repeat. Now this is effectively the same approach as in the math segment and the assembly segment, but there is something I'd like to accent here. It's subtle in this case, but we're no longer restricted to the operations of the CPU. And what I mean by that is that if we didn't want to multiply our result by a number, only by some wacky equation of a number, then we don't need to do it in multiple operations. We can just do it in a single line and let the compiler worry about how to most efficiently move them around. And that's the difference between C and assembly. In assembly, you have to describe each operation of the CPU exactly. In C, you have the powerful compiler on the side to help you. Where should the labels go for this loop? Let the compiler worry about that. Should our variables be stored in registers, cache or RAM? Let the compiler worry about that. Can we scramble our program into a single incomprehensible mess that no one can understand? Yeah. And then we just need to let the compiler worry about that. And so that's the difference, but there is one more language on our list of 3, and that is Python. Now this one I'll keep brief. This is what the code looks like, and it works in the exact same way as C. We just have our variables, number variable equal to a 5, and the result equal to a 1. And then we just loop over them, like so. There. Once again, we're done. We just print the result and we get the factorial. The reason why I'm going to keep this one brief is because there is only a single question that would be worth asking here. That's, why would anyone code in assembly or C when Python is this simple? And in order to answer that, we need to get back to the beginning. So first we need to start the CPU. CPUs have a lot of different functions, but the ones we're mostly interested in are the data storage, data manipulation, and operation manipulation. What this basically means is that first of all, you can store numbers inside CPUs. You can store them in registers, but there is also other methods of storing more numbers inside cache. Then we have manipulation, which basically means all the mathematics, includes stuff like addition, multiplication, but also some more specific ones, like conversion of integers to floating point or comparing numbers. Then finally, the thing that makes programming possible, operation manipulation. Because it's important to note that just like we can store the data, so the numbers, in binary, the code or the operations are also stored in binary. So you can move it around, and that is effectively the jumping. Then after machine code we have assembly. All assembly does is it just translates from ones and zeros to something a human can read, which just means instead of 0001, 00000010, we get move array x RCX. So all it does, it just translates the ones and zeros into human readable text for registers moving into and from cache or moving operations around. But to be more exact, assembly isn't really meant to convert the machine code into something a human can read. It actually goes the other way around. You write a simple text file, and then you take that text file, you give it to a program that's called an assembler, in my case NASM, and that assembler turns all of it into the appropriate bits and bytes and ones and zeros. Then those bits and bytes are packaged into a file, an executable file, which on Windows would be the .exe, and that's our program. Then next layer of abstraction is C. In C we use a compiler instead of an assembler, and what that basically means is that whilst an assembler is just used for translating from words to bytes, a compiler takes our code and creates a CPU program out of it. So for example, in C you can have a function, a loop, or an if. That is a more convenient way of writing something like this, or this, or this. And our compiler takes our input and converts it into the processor operations. That's how I generated the very large assembly code before. And then finally Python. Python isn't using an assembler or a compiler. Instead, it's using an interpreter, which means that instead of turning our text into machine code, instead we have a whole separate executable that just runs it. In Python's case, that executable is Python. Python is a language that's run by the program Python. That's why if you have Python code, you need Python installed on your machine to run it, and that's the difference. Machine code is basically the actual inner workings of the CPU that I've explained in the last video, this little bit right here. Then assemblers are the programs that take our text, written in the programming language assembly, and translate it directly to the machine code, the actual ones and zeros. Compilers work in a similar fashion, but with one additional step, where they take our code, which is once again text, they translate it to the processor operations, and then translate them into machine code. And then finally, the third category, the interpreters, which do not actually turn our code into machine code directly, but instead are a program that has to actively interpret it, running it internally. And those are the three main categories, and those are the differences between programming languages. You see, when it comes to programming languages, the difference is not just the notation. It's not just the words you use, the keywords, it's not just that. It is, in fact, the inner workings. They work in different ways, they can achieve different things, and that's why different people use different programming languages for different cases. They're all unique. But yeah, C is still absolutely the best. It's not even a contest, to be honest. Thank you very so much for watching. Hope you enjoyed the video. I'm so sorry it took me a little bit longer than normal in order to release this, but I am working on a really big video on the side, which I hope you will enjoy, and that's why it took me such a long time to finish this video. If you'd like to learn more about that video, then I would recommend my Patreon. And speaking of that, thank you so much to my patrons. Special thanks to Acronymus, Useless, Quasar, Macaroni, and Rocks. Thank you all so much for the support, especially as I need it right now. For State Secret, you can see the previews for that video on Patreon. Another thing, I stream every single day for charity, a series of live streams called Charity Checkups, which I would really recommend you check out. And for now, I suppose that'll be it. Thank you so much for watching, and have a great day. Bye.